Good afternoon to everybody. I would like to thank first Sasha, Bruno, and colleagues for inviting me to give this presentation. The title is Carbon Dioxide Fluxes from Diffuse Degassing in Italy, and I will show an overview of the results obtained by the studies performed in Italy in the last 2 decades by a research group led by Giovanni Chiodini, including me, Francesco Fondini, Stefano Caliro, and many other collaborators. Deeply derived carbon dioxide is released by earth degassing to the atmosphere from volcanical active areas, but also from tectonical activity areas, even when these are not affected by active volcanism. Diffuse emission, which includes soil diffuse degassing, degassing into aquifer, and widespread occurrence of gas vent, occur in both volcanic and non-volcanic settings, but characterize the emission of carbon dioxide in non-volcanic areas that will be the main object of this presentation. The widespread occurrence of carbon dioxide emission in tectonical active area was recognized since the late 70s by the pioneering works of Barnes and colleagues, and is testified by the occurrence of more than 1,000 carbon dioxide-rich gas discharge and groundwaters that are located in more than 50 countries. More recently, Tamburello and co-authors demonstrated a strong correlation between the areas with the highest probability of extensional faults or extensional earthquake occurrence and the location of carbon dioxide emission sites. Despite this early observation of Barnes, diffuse degassing at regional scale have been quantified in not many areas, and only in recent time. One of these areas is central and southern Italy. From the geological point of view, central and southern Italy are characterized by the presence of two major crustal and structural domains. On the western side, we have the Mediterranean domain, which is characterized by extension started several million years ago, resulting in a well-developed and mature set of faults and in a strong reduction of the lithosphere thickness. While the eastern domain is the Apennine domain and is characterized by the presence of the Apennine belt, by great lithospheric thickness, and by an active extension that causes an intense seismicity. The most macroscopic evidences of an intense process of carbon dioxide degassing in the region are concentrated in the Mediterranean domain and includes numerous gas emissions, travertine deposits, geothermal system, and active volcanoes. More in detail, about 270 gas emission sites were catalogued in Italy, and most of these can be considered non-volcanic emission because are not directly associated to the presence of active volcanoes. And this gas emission includes soil diffuse degassing, bubbling waters, and gas vents. The carbon dioxide release from this area were measured with different methods. For example, at lateral sites where the degassing occurs mainly through soil diffuse degassing with values of the flux rate that reach up to 2 orders of magnitude fluxes higher than the normal biological background, we used the accumulation chamber method, analyzing and elaborating the measurement with statistical and geostatistical tools. We estimated a total flux of about 350 tons per day. In some cases, like the Montecchie gas emission, there are areas like this reported in this picture, where the gas flux is too high to be measured using the accumulation chamber method. In this case, we developed ad hoc measurement methods for example, the combination of measurement of the gas velocity after the gas is conveyed into a pipe together combined with the measurement of concentration of gas into the stream. And this allowed to estimate the flux from vents like this. The last example is the Mephite gas ancento, that is an impressive manifestation forming a river of gas of more than 1 kilometers that is visible also from satellite image because the absence of vegetation. In this case, the emission is too strong and the area is very dangerous. So Chiodini and co-authors used the measured stream velocity and carbon dioxide concentration along a section of the river and coupled this measurement with physical numerical simulation of the gas plume to estimate the flux that resulted 2,000 tons per day for the entire emission area. Measured fluxes are available for 33 gas emissions in Italy and cover a wide range of values and give a total release of about 1.45 megatons per year, a value which represents an underestimation considering the large number of measured sites. Now, I will spend one slide to present what we think about the origin of carbon dioxide for this region. Carbon dioxide and medium concentration and isotopic composition of the gas released by the gas emission is a mixture between a mantle type gas and fluids deriving from limestone decarbonation. This is consistent with the presence of a metasomatized carbon-rich mantle that is due to the addition of subducted crustal material of the other plate into the mantle. The presence of this carbon-rich mantle is suggested by many authors on the basis of the composition of the product of the quaternary volcanism, which affected the Tyrrhenian side of the area. It's worth to note that the westernmost gas emission have an helium-3, helium-4 that practically coincide with the ratios measured in helium extracted from olivine and pyroxenes of Tuscan and Latium volcanic products. Now, we can also show that we have an enrichment of crustal helium moving from the west to east that was explained as due to the increase of the time of storage of the gas in crustal traps that are shallow in the Mediterranean domain and deeper below the Apennine domain. In addition to this primary and regional source of deep carbon dioxide, we can also consider the occurrence of an additional source that is due to the intrusion of magmas up into the lithosphere that can provide an additional source of carbon dioxide. Now, moving to the Apennine domain, we noted that this sector is characterized by very few gas emission sites, but this is due to the presence of large carbonate aquifers that are practically capable to dissolve any input of deeply derived carbon dioxide, preventing any arrival of carbon dioxide at the surface. For this reason, we investigated the diffuse emission in this area by investigating the deep carbon dissolved into the groundwaters of the Apennine. Using the springs allowed to investigate very large areas with a low number of points because each spring is representative of hundreds to thousands square kilometers. Because the carbon dissolved by groundwater is due to different contribution, we applied a method proposed for first time in 2000 based on carbon mass balance that allowed to estimate the different contribution to the carbon dissolved into groundwaters, starting from chemical and isotopic data. In this diagram, it showed the concentration and the isotopic composition for the carbon not deriving from the dissolution of the aquifer rock that we named external carbon. The data clearly show that a large number of aquifers are affected by the input of deeply derived carbon dioxide with an isotopic composition in the range of that characterizing the gas emission of the Mediterranean side, but also the active volcanoes and the geothermal discharge. By solving the carbon mass balance, we found that the largest part of the dissolved carbon is due to the dissolution of deeply derived carbon dioxide. The concentration of external carbon that were then converted into fluxes considering the water flow rate of the spring and the area of the hydrological basin that feed the spring discharge. The fluxes computed were used then to draw a map of diffuse degassing in Italy that is shown here in this picture. The map highlights two large regional degassing structures, one in central Italy, one in southern Italy, that we have named Tuscar-Roman degassing structure and the Campanian degassing structure. By subtracting the contribution of carbon dioxide due to the dissolution of biogenic carbon dioxide that was dissolved by the groundwater during the infiltration, we estimate a total deep carbon dioxide input of about 9.2 megatons per year for the two degassing structure. This amount is, for instance, higher than the yearly emission of the two largest active volcanoes that are located in Italy, so like Etna and Stromboli. The regional map of diffuse degassing pointed out also a clear correlation between the carbon dioxide degassing and the seismicity of the region, with most of the earthquakes that locate at the eastern border of the carbon dioxide flux anomaly. This will match with the proposed model of the presence below the Apennine of deep crustal geological structure accumulating carbon dioxide that can have a primary role in the seismicity of the region. In addition to this spatial correlation, we recently showed a strong temporal correlation between the deep carbon dioxide flux and the seismic activity. In fact, as is shown by the chronograph of the deep carbon dioxide dissolved in the Velino Springs aquifers that release the groundwater that circulates in the area of central Italy affected by two large seismic sequences in the last 10 years, we can note that dissolved carbon dioxide strongly increase with the occurrence of the most energetic earthquakes. We can also estimate the total amount of deeply derived carbon dioxide that enter into the aquifers, and this result of about 1,800 kilotons of carbon dioxide, a value that is very large and is of the same order of magnitude of carbon dioxide in volcanic eruption. Finally, I will spend few slides to do some consideration on the relevance of diffuse degassing from the global carbon budget. Summing the estimated fluxes of deep carbon dioxide dissolved into the aquifer with the carbon dioxide released by the gas emission, and considering also the data available for soil diffuse degassing in volcanic area, we obtain a total of 30 megatons per year for the flux for diffuse degassing in Italy. Comparing these estimates with the global carbon dioxide fluxes from subaerial volcanoes, tectonic degassing in Italy represents about values from 2 to 16% of the global emission from volcanoes. And considering the additional values related to diffuse degassing at volcanoes, we reach about 20% of the global carbon dioxide volcanic flux from subaerial volcanoes. Comparing the results obtained in Italy together with the data available for other tectonically active areas like the Western African Rift and Himalaya area, where we have carbon dioxide fluxes per square meters of the same order of magnitude, we can estimate roughly the contribution of the tectonically active area. Of course, this is a very, very rough estimate. If we consider, for example, the range of specific fluxes and the area interested by active faults, we obtain a carbon dioxide, a total flux of carbon dioxide from 0.4 to 9 gigatons per year. This is a very large values, and it represents 1 to 20% of the anthropogenic carbon dioxide emission. Of course, this is a very rough and simplified calculation, but put in evidence the necessity of, as much as possible, really quantification of tectonic carbon dioxide flux in many areas of the Earth that is still practically unexplored, to better constrain the real magnitude of diffuse tectonic carbon dioxide flux at global scale. I finish, and thank you for your attention.